All right, classic physics problem. Really what this comes down to is the impulse or the force of bouncing versus the force when things stick together. If you didn't put any thought into it, you don't have to write it down, you don't have to commit to it, but just what's your knee-jerk reaction? If we throw a ball at a block of wood, which would put more force on that block of wood? The ball that bounces or the ball that sticks? It's kind of a classic physics problem that often gets asked beginning in the topic, and then we do the math and see if you actually had the right idea. This all sorts of cool stuff here about preconceptions and prior knowledge. Often people guess incorrectly. Let's work through the math. I typed it on the document, but I didn't grab it all for this. What we're going to do, just to make things a little bit easier, is let's assume that it's the same mass for now. So the snowball and the rubber ball will have the same mass. And let's say that we throw them at the same speed. We'll call that speed v. The rubber ball is going to bounce back. So its second speed is going to be negative v. And we'll talk about what if it doesn't bounce perfectly backwards. And we're going to say that the snowball stops. So 0. Not the great notation, but with the audio there, hopefully that makes sense. It is an impulse situation, so we are going to use impulse is F times delta t, and that is equal to delta momentum. F times delta t is equal to delta mv, if we want to write it that way. This is a case where the m isn't changing, so F, I'll do two things at once. F is going to be m times delta v all over delta t. Now let's think about our rubber ball. Rubber ball, oops, I can't draw a rubber ball very well. It's going that way at a speed v, then after hitting the wooden block, it's bouncing that way at a speed of negative v. When we plug in our values, the force that the rubber ball generates is going to be m. Its v2 was negative v, subtract its v1, which was v, all divided by delta t. So our rubber ball is going to exert a force of negative 2 mv all over t. Our snowball, it goes at a speed v, and then it stops. So we set up our force equation for this one. Our delta v is going to be 0 minus initial speed of v all over delta t. We get a force of negative mv over delta t. For those, the negatives just tell us about the direction. They're both negative. The force to stop it would be in the opposite direction from the original velocity. So if they're thrown to the right, the force would be to the left. If we assume that they're the same mass, we get 2 mv compared to 1 mv, all divided by delta t. So just on the basis of that, we can see that the force of the rubber ball is going to be bigger. Generally speaking, when a rubber ball bounces, it would differ from ball to ball, but the delta t for the snowball is probably going to be larger than the delta t for the rubber ball. So the snowball, on the numerator, it's got 1 mv, then it's probably going to take a longer time to stop the snowball by the time it gooshes to a stop. So it's probably got a larger delta t, which overall would bring down the force. The rubber ball, to bounce, probably has a smaller delta t, which means bigger force, and the force it takes to stop it and turn it around doubles the force on it. Even if the ball doesn't bounce backward at a full v, but bounce backward at like negative half of v, we're still going to have a numerator that's bigger than the snowball situation. And just the physics of bouncing, it's probably going to have a smaller delta t, which also leads to a larger force. Bottom line is that when something bounces, the overall change in velocity is much bigger. That takes a larger force to make that happen. And if we were to factor in the delta time, bouncing usually takes less time. And as we talked about with car crashes, if you have less time, generally speaking, that's a greater force. So cool thing here, maybe you got the wrong answer and maybe you had good intuition, but generally speaking, when something bounces, that requires more force for a bounce to happen than it would just to stop it dead.